So the last part of this bit of the course really is probably the most useful in terms of real life stuff, and perhaps means the most for what we could imagine as being useful in the real world. And that is, we keep giving you questions, or I keep giving you questions where the population mean is already known. Like, we already know that the mean is this, and the reality is that that's unrealistic. It's unrealistic to know what the population mean is, because it means you had to go and survey the whole population or measure the whole population. And if you can do that, then there's no point doing most of the statistics on it, because you know everything. And so it's unrealistic in a lot of ways. Now, and perhaps it would have been nice to have gone through this first, but we need the other maths behind it. And that's to say that, like this example says, the company claims that the mean protein content of a 1 litre carton of milk is 39 grams. They didn't measure every one of them, okay? But they had to, they would have had to have taken a sample and made it from that. So it says, the truth of this claim could only be known by measuring every single carton. Not going to happen, okay? But we can draw some conclusions and some statistical conclusions about it. If we know some information, we can start saying, well, we're 95% confident that the mean is here, and it's not that the mean is 39. We could say we're confident that the mean is between 38 and 30 and 40. We can start doing some of these ideas. Okay, so we'll just follow through this. I know it's just reading from the textbook, but we'll just follow through this idea first, and then we'll have a look at some exact examples. So we could say that we did. We selected a sample of those milk cartons and found that the mean from that sample was 38 grams, not 39 grams. Okay, so you can see there they use that symbol. So it's a little bit like the symbol we saw where we did the sample means, and we had a capital X with a bar across it, and you put a number next to it and say this is how big the sample is. Well, if you take a sample, the notation we often use is to put an X with a bar on top. That's the sample mean, rather than the mu, which represents the population.
But aren't they the same thing?
Well, the reality, this is the reality. They're not. They, in theory, are the same thing.
So that's what we
Okay, but the whole point of statistics is that it's data, and data is never perfect. And realistically, we can't know that. We just don't really know the population mean. Okay, we could have done lots of testing over lots of years, and that's what it's come out to. And often that's what happens. They've got information from a whole lot of stuff, and they'll say, well, that is the population mean. We're going to use that as the population mean. But the reality is they can't actually really know that. Okay, we could use the census data from the other night and get an actual population mean, assuming that every single person did it on whatever the question was. We could do that. That would be a population mean, because it's the whole population of Australia. We could certainly do the population mean of the ages of everyone in this room, because if that's the population, it's easy to do. It's a small population, but it doesn't really, statistically, who cares? It's not a major thing. But when it comes to real stuff, where you're looking over thousands, hundreds of thousands, and millions and whatever of data, then it's sort of one of those weird situations that we say. Okay, so what this is saying is the company claims that their mean is, so their population mean is 39 grams, but a sample was taken and was found to be 38 grams from that sample. So this is that sample mean. Okay, it's from the last lesson we looked at graphing a set of sample means, multiple ones. What we've done is just taken one sample, so it's 38 grams. Okay, so is that enough evidence to say, well, actually, I don't think your company's right. I just took a sample and found out the mean was 38, not 39. I don't believe you. Okay, what we want to know, what do you think we want to know to be able to make that claim? Well, we need to know. Ultimately, we have to come to terms within statistics. We can never be 100% confident on something. We're using models, and we're making predictions based on possibilities and chance. But if I was going to make that claim, and I took a sample, I said I've taken a sample, and that sample's only got 38. Here's my data, and I've done it really carefully. What might the company first want to know?
How many?
Yeah, how many in that sample? Because if I've only taken 3, there's a fairly good chance I've picked 3 that are, a little bit lower than the mean, and that would give me that as the mean. And so it probably isn't very good evidence. But if I've picked a sample of 1,000 and I've measured all 1,000 of them and got the average of that, the mean of that, and it's under 38, then we're saying, well, that's a big sample, and the means come out on average to be 1 gram less than what you said. Well, I don't know, maybe there is something in there. So we want to go more than just saying, oh, I don't know. We want to come up with some sort of mathematical way to be able to deal with that. And the way we do it is we create these things called confidence intervals. So it's a space that we are confident, okay, that the actual real mean must fit within that. Okay? And we call that a confidence interval. It's a confidence interval for the population mean, which is much more realistic than saying the actual population mean is this. Okay? And so we put it between 2 limits, but we also assign to that a percentage of how confident we are. Okay, and we'll have a look at what that means in a second, but very, very commonly we talk about saying we're 95% confident that the actual mean must fit within this space. Okay, so if you look at this statement down the bottom, it says, consider the statement, we're 95% confident that the mean protein content of milk cartons is between 37 grams and 40 grams. Okay, rather than saying it's 39, we have a range that we're confident in. That range will be normally distributed, and the centre of it would be the mean that you've said the population mean is, but it could be a little bit either side. Okay, because we've only ever done it from a sample. Okay, so we have this thing called the 95% confidence interval, and we go back to this idea of z-scores. What we want to do is go back to our standard normal curve. Okay, so our standard normal curve is drawn here. Okay, 0 being the mean, 1 is a standard deviation. They haven't marked 1 on there as a standard deviation. But what we want to do is make it so that the area under there is 0.95 or 95%. Okay, that's what our aim is, because what we want to do is find the z-score that would be here, how many standard deviations above the mean, and then the z-score down here, how many standard deviations below the mean would we be so that the area in here is 95% or 0.95. Okay, now there isn't, I'm not going to scroll back to it, but if you can sort of visualise and think back to where the percentages, like the original curve that we looked at, and we had the 34%, etc. If you actually look at that, you can get very close to 95% on standard deviations. In fact, it comes out, and you can look at it on the calculator, all right, but it comes out to be 1.96 standard deviations above and 1.96 standard deviations below will give you that area. Okay, so our confidence interval ultimately is going to be the mean and 1.96 standard deviations above it and 1.96 standard deviations below it. So the other piece of information we need, and it's the other part that makes it a little bit, always a bit strange, is that we're going to need a standard deviation. Okay, because we need that standard deviation to be able to say, well, how far is that then? If it's 1.96 standard deviations, we need to know how many standard deviations that would be. So this part here looks really messy. Okay, it looks pretty ugly, but if we explain what's there, it's not too bad. What this is saying is the probability of being 1.96, Z is the Z-score being negative 1.96 and 1.96, between those two values is 0.95. Okay, what they've done then is plugged in here the formula for the Z-score. It looks different than before, but it's the same one. It's just that it's using the important things. It's using the sample mean. okay? Not the actual value. Remember before we did Z-score, we just said one value, what's the chance of getting a player that is 196 centimetres out of this set of data? That's just one player. What we're saying now is, what's the chance of picking a sample of 20 and the average of that 20, so there's the mean, being away from the actual population mean? So it looks different, but it's the same thing, so that's just the sample means. And remember that we talked in the last lesson about the standard deviation of the samples would be the standard deviation of the population divided by the square root of n. So we've just replaced those two from the Z-score formula. Okay, we've used the standard deviation of the sample means, okay, and the mean of the samples, okay, in there. So that's just the Z-score formula inserted here. Okay, so basically it's saying, well, the Z-score has to be between minus 1.96 and 1.96 to give us that 95%. Okay, we can then do some, we could say, well, hang on, let's times this out. Let's get rid of this and put it in both spots. So multiply it out to both there. So it's 1.96 lots of this, negative 1.96 and 1.96 lots of it over this side. Okay, and then get rid of this this mean here and bring that on the other sides. Why are we doing that? Because we end up with this formula here that says, here's our population mean by itself, here's the lower end of it, and here's the upper end of it. It looks messy, but what does it really read as? It says, well, here's my sample mean. If I take 1.96 times by this, okay, from it, all right, then it's just basically 1.96 standard deviations of the sample standard deviations below whatever the actual mean is. And here's my sample mean. I add that many across. Then I'll get 0.95. Let's put it into context. I'm going to skip that bit. That formula is given to you, I'm pretty sure, on the formula sheet anyway. All right. What I want to do is let's get a context to it so that it means more. So we'll go beyond all this. And we'll use this example here to help us. Okay, so here's our situation. It's a sample of 60 yabbies. They're taken from a dam. Okay, somehow, and this is still the control part, and we can't get away from it, somehow in that second little paragraph, we know what the population standard deviation is. How? Don't know. Okay, it's only estimated. It can only be estimated. Okay, so these questions are contriving that a little bit and saying, well, we know what the population standard deviation is. All they could really do is work out, there was 60 yabbies and use that and work out what the standard deviation of those 60 yabbies were and just assume that that's still the same as the rest of them. Okay, but we've been given that, so let's just take that on. The rest of it we've measured, we've found. So we've taken 60 yabbies and we found that their average weight, their mean weight, was 84.6 grams. Okay, we don't have anything about the population mean here. We just know that that sample had a mean weight of 84.6. What we would do when we're first learning about statistics, we'd say, okay, 60 seems like a lot. Maybe the average size of yabbies in this dam is 84.6 grams. Full stop, that's the end of the question. What we're saying now is we can go a little bit further with that and say, okay, hang on. I know that they vary by a fair bit. 16.8 grams is a fair standard deviation considering they're only 84 grams each. So they're quite varied in their size. So that 60, well, we could have picked a couple of big ones up. That might be a little bit inflated in this 60. So what we're going to do is construct this confidence interval to say, okay, statistically, the actual population mean must be somewhere between this. We're 95% confident it'll be between a bit below 84.6 and a bit above 84.6, and the amount above and below is this confidence interval. That's what we're doing. Okay, so if we have a look at what they've done in here, we've been given the sample mean. Our sample of 60 had a mean of 84.6. We've been given the standard deviation of the population. Okay, when you see the sigma by itself like that, that's the population. So the confidence interval, okay, and this formula is given to you, is our sample mean. So we start at 84.6, and we take off 1.96 of the sample standard deviations. Okay, remember the sample standard deviation is the sample mean standard deviation is the population divided by the square root of n. Square root of n, well, n was 60. Okay, so it's just the 84.6, the mean that we found, take away 1.96 of them, is the lower end of the scale. The upper end is that 84.6, that mean, plus 1.96, lots of it. Okay, so we put the n in, and they're all numbers. Okay, we just plug that straight into our calculator. Okay, and we get 80.3 and 88.9 on it. So what we're saying is, from this situation, statistically, we can say, and this is the wording that you need to use in a question like this. We can be, or we are 95% confident that the population mean weight of those yabbies is between 80.3 and 88.9 grams. Okay? What it's saying is the chances of us pulling that sample out from a population and knowing the standard deviation and getting a value that is 84.6, that's way below what the real mean is pretty low. Okay? If the real mean was actually 84.6, that was the middle, the chances of us pulling out, let's start that again. If the real mean was, say, 90, and we just happened to pick some smaller ones in there, the chances of us getting the mean out of 60 as being 84.6 is very, very low. Okay, that we would expect it to be somewhere within this space. Okay, so we're giving an interval. We're not saying what the population mean is. We're saying the population mean is probably between those two parts. Okay, now if you have a look just below, it shows us that in fact we can use a graphics calculator to just give us the confidence interval. We can just plug data in. Okay, so if we go to the instructions, hopefully we'll see calculator should work now and we can actually put it up.
It's still normal distribution, right?
Yeah, I've got to remember on the Casio how to do it. If you can't find it, I'll find it in a second. It's, found it? Yep. All right, so in this one, what do we need to do? It's that. Oh, except that it's supposed to say 7, isn't it? All right, we've got to go across. Yeah, so you hit the stat button, but you'll need to go across the menus to tests. Okay, and it's the Z interval one, so number 7 that you want to use. Okay, that's really big and awful to look at. So the things that we need to do is, I would have thought it would be on stats. Does it say stats? I'll calculate. Yeah. All right, so you need to have that you need to have it highlighted over here on the stats one, because it will actually calculate that. If you dump a whole heap of data into calculator, it will do it from actual data. We're not going to be doing that. So we've got to set it on stats, and then we just put the things that we know. All right, so I can't remember what the population standard deviation was, 16.8. So 16.8, I can't remember, was it 84.6? Yep. And we had 60. Okay, and what you notice here is this C level. Now that's set on my calculator, it might have been changed on yours or whatever, as 0.95, because you can make a confidence interval that is not 0.95. You could say, no, I want to be even more confident. I want to be 98% confident that it's within that range. What do you think that'll do to the range if I make it 98% confident that it's within that range? Will that narrow my range or widen it? Be careful with it. It's one of those funny, intuitive, weird questions which always makes you think it's going to be thinner. But in fact, what we're saying in this is we want to be more confident that whatever our sample was is definitely within the range. So if we want it definitely within the range, we'll widen the range because then it's more likely to be in it. So if it's 98% confident, think about your curve. It's going to be more standard deviations to get 98% within it. Okay? This is set to 95% because that's what this question asked for, but we could change it. So we'll hit calculate. And what it's given us is the upper and lower. So 80.349, 80.3 up to 88.9. Okay? It does give us this again. We already entered that data, but that's what the Z interval is for. So you calculate, and absolutely, if a question gives you all the information to use a calculator, use your calculator. Okay? But as you've sort of seen in other parts of the course, oops, I'm going to get that. It's questions deliberately written so that you can't just use your calculator. You do need to be able to use that. So if we go to an example of that, just find. No, I thought they would have had one in here. No. I thought they might have an example. I'll have to find one to show you what I mean. We will, but it's in the next topic. That's to do with this discrete.
So is this our last?
This is it. D is the last part. Yes. Yes. Okay. So, be aware, and I'll find a question perhaps and give it to you to sort of have a go at later, and I'll find there should be some in here as well. You can use a calculator, absolutely, and in fact, lots of times it's just perfectly fine. Just use your calculator, there's a confidence interval. Okay, so it's quick. But there are times where you might get a question and you have to actually go through the process of doing that, using that formula. So I'll find a question later and highlight what I mean by that. But the other thing that, the use of that is more than just saying, well, what's my chance of the mean being in here? I could use it to actually also test some ideas. So this quality control idea that we've already been talking about. So this example says volume of milk dispensed has a mean which can be adjusted, different to the other questions. We can adjust the mean. But it has a standard deviation of 10 mils, which is fixed. So they know that the machine varies in that sort of plus or minus amount, which gives us a standard deviation of 10 mils. But we can change the mean. We could say, well, I actually want to fill them with 300. Maybe it's a machine that can be used to fill different size cartons. So you can set it to fill 1 litre or you can set it to fill 2 litres or whatever. So it's supposed to have been set to 1,005 mils. Okay, that's what's supposed to have been set at. But what the quality control officer does comes and says, right, I'm going to test 25 cartons and finds that the mean of that 25 is only 1,002 mils. So it's a little bit less. Okay, so the first thing that they've done is say, well, let's construct a confidence interval for the mean volume that's being dispensed by the machine. It's supposed to be 1,005, but let's forget that. Let's just say all I know is that the volume that we got from our sample was 1,002. So your confidence interval, okay, if you look at the values that they've put in, I can't see which one's the TI, doesn't matter, I think either of them are though. But we're saying that our, this is the Casio, but it doesn't matter. Our confidence interval is 0.95, different spot in the Texas. The standard deviation that we use is 10. Okay. The sample mean we found was 1,002. You'll notice there's nowhere to put the actual population mean because we're not using that. We're saying where does the population mean really fit? And our sample is 25. Okay, and what that gave was a confidence interval of 998.1 to 1005.9. Okay, so if we took a sample of 25 and found that the mean volume was 1002 mils, we're 95% confident that the actual mean value for that population sits between this. Okay, and then it says use this 95% confidence interval to assess that claim that the volume is actually 1005. Okay, well, 1005 fits within that. It's fairly close to one end. It's fairly close to the upper end, but it's still within the 95% confidence interval. So have a look at the wording, because this is the sort of wording you have to answer them with, and it's sometimes hard to go with that, because you look at that and you go, oh, it's pushing the limits, like it's up there. I mean, I know it's nearly 1006, so it's not too bad, but it is upper in the higher end of this confidence interval. But mathematically speaking, 1005 lies within that confidence interval, the 95% confidence interval, despite the fact that the sample mean is less than 1005. We don't have enough evidence to reject the claim. So if the machine is telling us that its mean is 1005, we can't statistically discount that. Okay, it could well be. All right, you might be, if you're a quality control officer, you might be saying, I'm going to do another test. But that's how they work. They work on statistics like that, and they would say, no, it's within that confidence interval, it's fine. And we walk away. Okay? If we increase the number of cartons, what do you think that will do to the width of the confidence interval?
Shorten.
Yeah, it will shorten it. Because if we have more cartons in there, then we are going to be more confident that we've got the real mean. Okay? So by increasing the number of cartons, we'll make the confidence interval shorter. If we have less, it's going to be wider. If we want to use a different confidence level, then we would need to consider what happens. If we wanted to be more confident, we have to make it wider. Then we can say, oh, it's definitely going to fit through there because I've got a really wide interval. Okay? If I go to a 90% confidence, I don't need to be as confident, then I can narrow my window down a bit. But that might not be useful because you're only 90% confident then. So you can vary those. And I'm going to check in a minute because they changed the course at some point. I can't remember whether it changed from being it's always going to be 95% or it can be different amounts, or whether they changed it back the other way. I just can't remember off the top of my head, so I'll check that. So the questions in 9D relate to all of those things. It does take a bit of practice, one on the wording, thinking about how you're going to word it, and thinking about what the numbers mean. The maths, most of it's chucking stuff into a calculator and you get numbers. But you have to know what the numbers are telling you and how to explain that in an answer. That's the challenging part of it. Okay? That should cover most bits. There is the bit that I need to find. So I'll try and find a question maybe a little bit later on, or give you an example in the first 10 minutes of next week, even though I said I wasn't going to take your time, but 10 minutes or whatever, just so that you can see one algebraically. Okay.